This is Lab 4 Oscillations. Introduction. The purpose of this lab is to track the oscillation of an object that is dangling from a spring and to track the energy changes in the system using a model. The result of this lab is that while the object oscillates on the spring, the forms of energy are constantly changing value following a pattern. However, the total change in energy, delta E, remains zero. Principles used in lab. This lab uses the principles of the velocity update and position update formulas, the energy principle, F net is equal to F grav plus F spring, and F grav and F spring. Experiment. For the experiment, an object attached to the end of a vertical spring was let go from an initial position in a way that caused it to start to oscillate. As this is happening, the object is undergoing multiple changes in its internal energies. Tracker data. This is the tracker data that was used to predict the movement of the spring's object for the model. Observed data. The data observed in the experiment and the model shows the changes in energy over time. The experiment only tracked the movement of the object as it oscillated, and so the purpose of the model is to be able to closely mimic the experiment's movement to show a representation of how energy changed in the experiment. With the model being very similar to the original experiment's position data, it can be inferred that the energy data of the model is close to that of the experiment. The energies in the model change over time in a wave-like pattern, however total energy change remains zero. Computational model. The computational model calculates the change in energy over time for each energy value using the position and velocity data gathered by the experiment. The code works by taking an X and Y position data from a CSV file and then using the velocity and position update formulas in the formulas for F grav and F spring to find the data needed to calculate delta K, delta UG, delta US, and delta E. Errors. This experiment has many errors that make the data not perfectly matched between the experiment and model. The main error is that the model cannot perfectly match the position versus time for both X and Y values, meaning that all data gathered from the model will differ from the real values of the experiment when it predicts the energy changes. There's also some human error in how the video used for the experiment has a human interacting with the system to start the oscillation, which makes the initial position and velocities not perfect matches when gathered for the model. However, at the end, the model is close enough to the original that it still has a mostly correct prediction of the energy changes. Computational models. These are the three computational models used to show the accuracy of the model compared to the experiment. First, have the X graph, the Y graph, and the actual visual model of how this spring would move. What does it mean? For your model system, is the energy principle satisfied? Justify your answer by discussing briefly your plots of energy changes. The energy principle is satisfied by my model. The energy graphs all three energies in the system, and the total energy, delta E total equals zero. The three graphs form waves in which the delta E graph and the delta E spring are always on opposite sides from each other, but one tends to be smaller at that time. To balance it out, delta K is also on the side of the currently small energy, making the energy of all three cancel out to zero, which is equal to delta E total. Using the data you obtain in Tracker, make two separate estimates of oscillation periods first, by estimating the period of oscillation from the X position data, and second, by estimating the period of oscillation from the Y position data. Compare the two estimates and discuss. The period of oscillation for the X position data is about 1.5 seconds. The period of oscillation for the Y position data is about 1.5 seconds. The estimates are the same, which means that the object does a full oscillation in both directions in about 1.5 seconds.